And I also realized this is our last day together. I feel like I just came to know you guys, but it's our last day here. So we're gonna do, thank you. We're gonna do 2 sections on theory in the morning, and then we're gonna finish the tutorial this afternoon where we're gonna go through the model, and then I've asked the famous professor Shankar Paresh, who is a professor at IIT Kanpur. He was a postdoc for me back when I was at Maryland. He's going to talk on a paper that actually was the reason why I hired him as a postdoc, because I think it's a really cool paper. So he's going to do a presentation on that, and I think it's a great example of how to use agent-based modeling to solve a problem of managerial interest, right? And also kind of has some social science implications as well, I would say, right? So that's what his talk will be this afternoon. So we're actually going to do a full day today, which also probably a good reason why we start a little later. So it's going to be 2 theory sections, the tutorial, and then the special presentation by Dr. Paresh, right? So let me pick up where we left off. We were talking about all the different so now, we kind of started to build this model from the ground up. We've talked about what agent-based modeling really is, and now we're kind of tearing it back apart again. And we're talking about all the issues that affect agent-based modeling, right? And things that you might want to consider. And so one aspect that we sometimes don't think a lot about, but is important to consider, is how much cognition is our agent going to have, right? So a lot of times when we think about it, we think about these rules where the agent just simply sees an input and takes an action, but there's much more complex cognition that we could give to the agents, right? And so what we're going to call cognition is the process by which agents take inputs, make a decision, and then take an action as their outputs, right? The more complex the cognition of an individual agent, the more computational effort is going to be required, right, often. And so usually, the more complex the cognition, the fewer the number of agents you can have in the model to run the same amount of results, right, in general. But that's a loose guideline. There's some reasons why that's not always true, but that's a loose guideline. So I'm going to use, my favorite AI textbook is back from 1995. Actually, they've released a couple of versions since then. I picked up the 3rd version the other day. It's still pretty good. But it's the Russell and Norvig Introduction to Artificial Intelligence, but a modern introduction to artificial intelligence. And one of the things I like about that particular textbook is that they use an agent framing for artificial intelligence. Everything is discussed as if an artificial intelligence is an agent. So it works really well for talking about agent-based modeling, where we're again talking about agents. And Russell and Norvig discuss essentially 4 types of agent cognition: reflexive, utility-based, goal-based, and adaptive. And we're going to go through each of those in turn. So reflexive agents are simple rules where agents simply react to what is around them. Often these are represented by simple if-then rules. You can think of this as the classic stimulus-response kind of framework, right? In biology, we often think of the fact that animals, you provide them with a stimulus, they give you a response, right? And usually in the simpler animals, right, the animals that don't have as complex brains as humans or primates, that response is almost completely predictable, right? And so agents are kind of in that space as well. And let me show you an example. So we're going to go and use the traffic model a little bit. And you've seen the model a little bit before. It's very appropriate considering the fact I was stuck in traffic for 2 hours yesterday. And in this model, right, the rules are very if-then, very simple, right? Give me a second to bring it up. I should have started this up before. And I showed this model, but we hadn't really talked about it before. And now that we have some experience building models, it should be possible for us to understand what's going on. So here we have the simple model. If you remember correctly, there's no difference between the red and the blue cars, except for the fact that we're highlighting the red car so we can see it easier, right? And all the agents do in this model is speed up until they see a car in front of them, and then they slow down. And now that you know kind of what NetLogo code looks like, let's take a look at the code tab. So in the code tab, down to Go, which you know is the place to look, you'll see that this basically is all the code that you need to know about, right? And what does it do? It does ask turtles, let car head be one of turtles on a patch ahead 1, right? So basically, all the cars are facing this way. And so car ahead is going to be, patch ahead is going to be the patch that you're about to move on to. Give me one of the turtles off of that patch, right? So I'm just going to look at one of the cars. It really doesn't matter if it's the car that's like closest to me or not. This is just a simple way of doing that, right? Because roughly they're all going to be about the same. If there's nobody ahead of me, right, then speed up, right? If there is someone ahead of me, then slow down my car ahead, right? And what does that mean? Well, we have to look at the code to see that. So it's this code down here. So first of all, speed up is easy. We're going to set our speed to speed plus acceleration. Slow down is set our speed to the speed of the car ahead minus deceleration, right? So we're braking behind that car ahead of us, right? And then finally, if you look back up here, if we're going too fast, we set our speed to the speed limit. If we're going too slow, we set our speed to the minimum speed, right? So there's a minimum speed we have to crawl along at. There's a maximum speed. And then finally, we just go forward our speed, no matter what it is, right? So this is an if-then kind of purely what we would call a reflexive agent role, right? Where all that matters is that the agent is just saying, if there's something ahead of me, then slow down, otherwise speed up, right? But that's not really a very complex cognition. So let's talk about the next type of cognition. So the next type of cognition is utility-based. And in utility-based cognition, agents are given some utility function, and then they are trying to maximize that utility function, right? So in this case, they kind of have the freedom to choose what actions they want to take to maximize that utility function. Usually they're limited in the freedom of actions they're going to take. So we're going to look at a traffic version where they can choose their own acceleration and deceleration rates, or choose their own speeds, right? And we're going to see if we can maximize an aspect of that, right? So this model is in the models library under the textbook section, and it's called Traffic Basic Utility. And if we open that, if we go down to the Go, what happens, it's basically the same, except for instead of, if you slow down, you slow down. But if you speed up, you adjust your speed for efficiency, right? So what does that mean? Well, there is a new slider that's set in here, which is efficient speed. If you think about this, kind of the idea is that for almost any car, there is a speed at which it will travel that will maximize its fuel consumption, right? In most cars, it turns out that's somewhere around 80 kilometers an hour, right, to maximize the fuel consumption, right, so that you get the most kilometers per liter, right, essentially. I'm never able to do the reverse that you sometimes 100 liters per 100 kilometers per liter, right? I like to think of it the other way around, kilometers per liter, right? So, anyways, so there is usually a speed for any car that maximizes that. So let's assume that for the cars on our road, it's 0.5. It's just an arbitrary unit, right? So what is the model going to do? It's going to try to adjust the speed to that efficient speed, whatever it is. Only in the case in which there isn't a car ahead of it, right? If there is a car ahead of it, it has to brake, right, no matter what. But if there isn't a car ahead of it, it will try and find a speed, and it will adjust its speed up and down to try and get to that efficient speed, right? So we're giving the car kind of a little bit more complex cognition. So in this model, what is interesting, as you will see, is that unlike the other one, we can eventually adjust that efficient speed to actually even prevent traffic jams from occurring, right? Because another way to think about it is, rather than thinking about efficient speed as being an efficient speed for fuel efficiency, you can think about it being as an efficient speed to prevent congestion. Now, in this one, it's not at that, but if we hit setup, sorry, I'm going to have to adjust it first and then hit setup. You know, if we set the speed just right, the efficient speed right now, then essentially everyone can just move at that efficient speed, right? So, and maybe, you know, it's hard to say whether or not people are actually moving faster in this world than they are in the world with the traffic jam or not. But there probably is some speed just below when a traffic jam forms that probably results in the maximum efficient speed, right? So this is a utility-based model, right? In this particular case, the agents are given a function that they're trying to maximize, and then they're maximizing it, right? So that's another example of agent cognition. Now the next example is goal-based agents. So a goal-based agent, we're not trying to maximize a particular utility function. We're just trying to achieve a discrete goal. Now, these are clearly related, right? Like if I can characterize my goal as being something where I have a function and there's one peak in that function, right, then I can cast the utility-based goal as a goal-based function, right, and vice versa. But there are sometimes when you can't easily do that, right, where a goal-based function is just, I need this thing to happen, and I don't really care how you get to that thing, I just need that thing to happen, right? In our case, the one we're going to look at a slightly more complex version of the traffic model. So we're going to look at ones where essentially the goals are very simple. Every morning, people wake up and they try and go to work. Every night, they get done with work and they try and go home. So their goal in the morning is to get to work. Their goal at night is to get home. And that's it, right? It doesn't matter how they do it. And they're going to move around on this two-dimensional grid instead. And this is actually, interestingly enough, this model was originally created not to talk about how people move around, but actually it was built to think about how timing of traffic lights affected patterns, right? But we're going to ignore that part of the model completely, right? The nice thing, that's a good thing about agent-based modeling. One of the best ways to build an agent-based model is take a model that has some of the componentry you need, and then just build the componentry that you need on it, right? Rather than starting from scratch. A good programmer copy and paste most of their code, right? And so that's essentially what we're trying to do here, right? Anyways, we're gonna take this code that was built for a different purpose, and then we're gonna create it. And so what you're gonna see, if you look at the code, is that the turtles have a work, a house, and a goal. Work is where they work, house is where they live, and the goal is where they're trying to get to, right? So that switches in the morning and in the evening, right? And if you go down to the setup a little bit, you'll see that the goal candidates right, where's goal candidates? It's up here. Goal candidates are any patches who are next to a road, right? So we don't want the house to be like in the middle of this area because then they're never going to go to their house, right? They can't get there. So they're ones that are next to the road. So they're going to choose a workplace that's next to a road and a house that's next to a road. And they're all randomly chosen, right? But you could think about setting them up to be specifically chosen. And one other small thing is that their work can't be at their house. We're assuming they don't work from home in this case, right? Okay. And then what happens, if you look at the Go routine, is they're going to identify the next patch that is closest to the goal, and they're going to head in that direction, right? And then they're going to move forward, and they have to obey all the kind of rules of not running into other cars and stopping at the stoplights and everything like that, right? But that's essentially what they're going to do. Yeah? Okay, yeah. This one right here. No, so they don't try different ones. They just choose one. The candidates are already specified, right? So if you look above, right? So the goal candidates, right, are patches with P color equals 38, which is that tan color, right? And any of their neighbors are white, which means those are the roads, right? And so we've identified all those patches now as the potential places. And then the house is just one of those. And the work is one of those that's not the house. So it doesn't have to, we could do it like, I think what you were saying, which is like, keep choosing random patches until we found one that met this criteria. But it's usually faster if you know what the criteria are, right, and you can easily enumerate them, to identify the set of all things that meet that criteria and then just choose one of those, right, from that set. Does that make sense? Usually that's more computationally efficient. So if we go to Go, the thing that's kind of hiding all the details here is this face next patch. Right? And face, by the way, I don't know if we talked about face XY, but we didn't talk about face. So face is a piece of it's a command that takes an agent rather than a coordinate, and it will have the car face that agent. And in this case, it's a patch, so it's always going to face the center of the patch, right? So it says if goal equals house, and I'm here, right? Then set my goal to work, right? So if I'm at home, then I'm at home. I don't need to do anything. Set the goal to work. If my goal equals work, and I'm here, then set my goal to house, right? And this command, this is a little tricky command that we haven't seen yet, so it's useful to talk through. Neighbors for of work. So work is my goal, my patch that is at my work. Neighbors for gives the up, down, left, right of that neighbor, right? So not the ones in the corners, right? Actually, it's a little bit, we'll talk about this in just a second, but it's the difference between a von Neumann and a Moore neighborhood, right? Patch here. So if the patch I'm on is a member of this set, and this is a command that allows you to check to see if something's a member of that set, right? And that was my goal, then I'm there, right? So I'm going to set my goal to house. If not, I'm going to let my choices of which patch to face next be neighbors with P color equals white, red, or green. Red or green are the traffic lights, right? Even though they're represented as patches, we're assuming they're driving under the traffic lights and not through them. But that's the basic idea, right? So, and then we're going to choose of those choices the one that has the minimum distance to my goal, right? Does that make sense? So distance calculates the distance between an agent and another agent or a patch, right? And goal of myself, this is a thing. So right here, we're asking for the patches, right? We're asking each of the patches to check something. And so myself is the thing that's calling that, which is the turtle, the agent, right? So the goal of myself. So let choice be the min one of the choices, which were these neighbors, who minimize that distance, right? Essentially find the patch that's the closest to the goal that I'm heading toward, right? And then face that one. Distance only takes one argument, right? And that argument is a patch or an agent, because distance is a reporter that is calculated for that agent, right? So what choices is going to do, right? What min1 of is going to go over every patch and choices and iteratively call this function on it, right? And so choice 1, the patch in front of me, right, is going to call distance on the goal of myself, and myself is whoever called patch 1, which was the turtle, the agent that we're currently talking to. So so myself is a unique command in NetLogo. I don't know if I know of any other language. Well, they have they're parent in some languages, right, which is the thing that called me, right? Self in Python, yeah. So this is essentially equivalent to self in Python, right? But it doesn't exist in a lot of languages, this kind of structure, right? So it's the thing that called me is what myself is, right? Actually, self is different. Isn't self me versus the thing that called me? So myself is the thing that that instantiated me, that called and invoked me. I believe self in Python refers to the object that is actually currently executing. But I could be wrong about that. Okay. Because there's a difference. You actually do have self. You can do self in NetLogo too as well, which is me, right? Or myself, which is the agent that called me. But we kind of ignore self because, yeah. But the important point is calculating the minimum distance between those two, right? So this should achieve our goal. Now, this is just one way to achieve the goal, right, of what we want. We could have written the code in very different ways, which is what makes a goal-based agent interesting, right? Because there's many possible ways we could have written the goal to achieve the code. And if we were really smart and wanted to do it, we could write a machine learning algorithm that tried to figure out what the most efficient way to go from my home to my patches, right? And actually, this algorithm has a bug. I don't know, can anyone think about what this bug might be? And maybe, I don't know if we see any of the agents doing it. Occasionally we do. Yeah, I think there's one that's doing it a couple times over here. Right there. He's fallen victim to the bug. So there are points in the space where if I go forward, right? If I'm standing in my space and I look around, the patch that's closest to my next goal is in front of me. But as soon as I step forward, the patch that's closest is actually behind me, right? So I keep going like back and forth and back and forth. And the reason why is because for him, probably his goal is actually directly above him, right? And so he needs to choose a direction of going one way over the other of searching around. Now, there's plenty of solutions to this in computer algorithms, right, that will prevent you from running into this bug, but we didn't want to implement them just for a quick example in a textbook, right? So we left it in there, and we leave it as an open exercise that if you want to fix it, you can do it, right? There's things like something called taboo search, which basically says that you can never go back to the same place you were before, right? And things like that you could use to kind of address these kind of problems, right? Anyways, that's an example of a goal-based agent. Does that make sense, kind of? Okay. So the next and the most complicated agent is an adaptive agent. And this kind of, if you remember correctly from when I talked about, goal-based agents you can kind of write in other modeling formats, right? You can write you can use constraint programming, for instance, to write goal-based agent logic. You can write utility-based agents in most econometric theories, right? You can do simple instinctual agents in game theory, right? Like all these kind of things exist in other formats. Adaptive agents are one of the few that is extremely difficult to write in any format that's not an agent-based modeling language, right? Agents in an adaptive agent can change not only their decisions, but their strategies. And what do I mean by a strategy? I mean that if I take the micro state of the world at time t, and I take the micro state of the world at time t plus k, sometime in the future, right? The agent will deliberately take a different action at time t plus k versus time t because they have learned from their past experience, because they learned from time t at some point, right? That's what we mean by a strategy, because a strategy is the fact that given the state of the world, I'm going to take action X, right? And I've changed my strategy from past experience. And if that's the case, then we say that the agent is adaptive, right? The action that agent takes, given the same environment over time, may differ based upon their past experience. So let's talk about one of these examples. So one of these is the traffic basic adaptive model. Actually, I like the individual adaptive one better. This one adapts everybody's speed. This one adapts each car individually. Okay. So you see there's a number of things now that are different. Number of cars, initial acceleration, deceleration, speed limit, they're all there. And then there's tests. That's brand new. Right? And what you'll see, if you go down, is we've allowed two different types of goes now. We have go and we have adaptive go. And go looks just like it did before. It's the exact same code from the traffic basic model. Right? Adaptive go is very similar, but it first has the turtles adapt, right? So what does that mean? It means that they're going to set the speeds. They're basically going to create a list of how fast they've been going at every time, right? And then if the time between the ticks is greater than the ticks between test algorithms, so every number of ticks, right? They're going to calculate on average how fast they went, right, since the last time they tested the results, right? If their mean speed is greater than the best speed they had before, then they're going to set their best acceleration to that acceleration and set their speed to be to that main speed, right? If it's not, if it's worse, if they did worse than the last time period than the time period before that, right? Then they're going to set their speed to be 0.1 times the mean speed plus 0.9 times the speed to meet. This kind of just gives you a weighted average, right, of what the current speed to beat is, right? So what happens is, let's imagine the reason why we're doing this is, let's imagine that we set our acceleration at a certain speed, and it's doing really well, and then it starts to do poorly over time, right? For whatever reason, right? Maybe we need to, maybe the road conditions have changed, maybe there's more cars on the road, whatever, right? If that is the case, right, then we need to start penalizing what we thought was the speed that we got from that acceleration. So we're going to slowly, but we don't want to penalize it because it might have just been we might have just run through a bad part of town, right? And that was the reason why our speed was bad that time. So we don't want to penalize it all the way, so we just penalize it by 1/10. We weight it by 1/10 and add it in, right? And we set our acceleration to the best acceleration so far, right? If, once we've done all that, right, regardless of what the answer was to all those calculations, we're just going to modify our acceleration a little bit up and a little bit down, right? Or a little bit up or a little bit down. If it's less than 0, we'll set the acceleration to 0, which still won't do very well, but we're going to try it. And we're going to reset that speed counter, right? So can you kind of understand what this is doing at a high level, right? Essentially, it's saying, I'm going to run my model for a little while. I'm going to see how well I do as a car, right, at that speed, at that acceleration. And then after that's done, I'm going to check, was that better than any other time when I ran the model, right, when I ran that at speed? If so, I want to take that acceleration as my new acceleration, right? I'm going to keep that acceleration. If not, right, then that's okay. Maybe that was just a fluke. But I'll kind of penalize my previous, what I thought was the speed I could achieve by a little bit, right? And regardless of all that, I'm just going to mutate my acceleration a little bit just to see if it helps at all, right? And then I'm going to run the same test again. So I have questions. I know it's a little bit complicated, right? But you can understand that essentially what's happening is that the agent is changing its reaction to the world around it, right, by adapting its speed over time based upon the same situations, right? Even given seeing the same speed, at times it's going to wind up in a different acceleration, right, because of the fact that it's constantly experimenting and constantly checking it out. So what do you think happens when you run a model in which all the cars are adapting their acceleration? Any ideas? So you know the traffic basic model. Everyone gets stuck, right? How many people think that the adaptive traffic basic will wind up in a traffic jam? How many people think it won't wind up in a traffic jam? There will be no traffic jam. Okay. How long do you think it'll take to get to no traffic jam? Any ideas? No? Okay. Let's see. So you can see they're all slowly adapting their traffic, their speed. So far, it's still pretty much a traffic jam, but actually, if you look at that blue line, so the blue line on the left graph is a good indication of whether or not we have constant traffic jam, because that's a measure of whether or not the minimum speed of the system is going to zero, right? If the minimum speed of the system is going to zero, that means there's a traffic jam somewhere, right? So now there's still kind of a traffic jam there. But there we start. Oh, now one got back again, right? And still got one. So let's try and run this for a little longer, see what happens. Eventually, we do get to this world in which there are no traffic jams, right? And everyone's moving at top speed, too. Now, part of that has nothing to do with the actual values of the accelerations. If you look at the graph on the right, which shows what the acceleration values are for the different cars, they're about the same, honestly, right? The big difference is by going through these different acceleration values over time, the cars are actually eventually able to space themselves out enough that they can get into a free flow system, right? So what's interesting and fascinating about this model to me, right, is that the actual thing they're changing has little to do with the final outcome, right? In the final state, the values of I could change all the acceleration values right now and it wouldn't matter, right? Because they're spaced out enough now that they're just never going to run into each other, right? And I think that that's an interesting kind of result. That sometimes adaptation, right, can put you into a state where the actual adaptation no longer matters, right? But we couldn't have done it without the adaptation, right? The adaptation allowed us to kind of keep moving and changing the distances between the cars in order to allow this to occur. Okay. So that's all about, so far we've talked a lot about agents. I want to talk about environments. Environments are different, right? And there are a number of ways to represent your environment, right? There are three kind of ways that we think about normally. Patches, which is the kind of way we've been talking about a lot. Another way to think about environment is a uniform environment, right? So you could think about just making the world one big patch, right? And then every agent is just located on the same patch within that world, right? That's pretty easy to imagine. And then you can think about external environments. And what I mean by that is by drawing data from outside the agent-based model to create your environment in some way, rather than having the environment part of the agent-based model. I keep leaving my clicker. So, four of the most popular types of environments are spatial environments, network environments, 3D environments, and GIS environments, right? Spatial environments, these are the ones we're used to seeing that we've seen already, right? It's exactly that description I was mentioning. They're essentially, in most agent-based models, we tend to think of two different types of environments. Either what's called a von Neumann environment, after von Neumann, who invented the ENIAC computer, right? He described a lot of work on cellular automata, and he built a lot of his models like this, where the patch in the center was connected to the patch to the north, south, east, and west. Moore, who's another researcher, thinks of the environment instead as having 8 neighbors, right, on any side, right? Easy way to remember, the Moore environment has more neighbors, right? So it's a simple little clue to make it easy to remember the difference between the two. You can also do hex cells. People, any idea why people might like a hex lattice as opposed to a square lattice? Square lattice has one interesting problem with it. So the square lattice, yes. So the distance to the 8 neighbors of a square cell is different for each of the for the corner neighbors versus the middle neighbors. In a hex, the distance from the center of the cell to all of its neighboring cells is exactly the same, right? So some people like the hex ones better because they have nicer properties, essentially. Let's put it at that, right? There's no built-in hexagon. You can't just click a button in NetLogo and create a hexagon environment. But there's an example set of code called hex cells that I would recommend you take a look at that shows you how you can remap the cells that are in NetLogo into a hexagonal pattern, right? And so you can kind of create a fake hexagonal network in NetLogo fairly easily. And the only difference is you can't use all the patches here, patches there. You have to start using your own code that calls the hex patches instead in the appropriate way. NetLogo is essentially a continuous space with a discrete grid laid on top of it, right? So you could just create use the NetLogo environment itself as a continuous space if you wanted to, and just ignore the patches, right? And then you could get a continuous space as well. Some people like continuous spaces. The only tricky part with using continuous spaces is boundary conditions, right? So if I have in any case, I have a boundary conditions. We've talked about the toroidal boundary conditions, right, where the right side of the world matches the left and the bottom matches the top. You can think about a bounded topology. The ants model, which I haven't shown you, uses a bounded topology because it's assuming that the ants can't run off the top of the world and come back around to the bottom, right, that they're living in a real world. But you can actually think about also an infinite plane topology, right? So imagine a world in which the agents can go on forever in any direction. Well, how do you do that when you only have a discrete space, right? Well, the easy way to do that is you just think of your discrete world as just looking into the infinite plane, looking into a section of the infinite plane, right? And so if an agent walks off the edge of the world, you just mark them as hidden, and you keep recording where they are in their own state variables instead of in their x-coordinate and y-coordinate variables, right? So there's a great example of that I always like to pull up, so we'll bring it up, which is this random walk 360 model. So in this spot, there is an infinite world. The agents are literally just moving randomly, right? And we're tracking how far they are away from the center of the world where they all start, right? And you'll see that as they get towards the edge, one of them just walked off the edge of the world, right? We're still able to track where they are, right? And why are we able to do that? Well, if you go into the code, you'll see that there's this XC and YC, which is their unwrapped x-coordinate, y-coordinate. And so when they do the go, they actually modify their XC and their YC first, and then if there's no patch at that coordinate, then they just hide the turtle, right? And if there is, then they show the turtle and they update their x coordinate, y coordinate appropriately. All right. So this allows you to kind of use the NetLogo view as a view into an infinite world, essentially. Right? Does that make sense? Oh, you could. They would just show up stuck on the edge of the world, right? So the visualization's bad if you do it that way, right? You could do it, right? There's just no problem. Yeah. So if I take that out, we can't even do it real quick, right? Actually, I think I have to do it this way. Okay. You see? There's just a bunch of turtles stuck at the edge of the world, right? So that's what happens. And that's not really where they are, right? They're actually far off the edge somewhere, right? Okay. So network environments we've talked a lot about in this class already, right? So I'm not going to spend a little time here. But I just want to mention that you can draw any kind of network you want in NetLogo, basically, right? Because we have the ability to draw the links any way we want. You can do what's called a scale-free or preferential attachment model. You can do a random network. You can do a small world network. Or you could read in data from a file for a network you've already described, right? And so if you remember back to like that Twitter model I showed you in the very first class of individuals adopting the purple hat, that was actually a real Twitter network that we read into the model, right? There's some cool visualizations of networks just to explain. So that's actually a real world network, right? This is actually the preferential attachment model as implemented in NetLogo, which corresponds to this paper from Barabasi and Albert from 1999 in Science, where they first built it. They show in that paper, by the way, that the preferential attachment model is actually a very good model for representing a lot of real-world social networks, right? And then Watts and Strogatz have their small world network, which is also implemented in NetLogo. And that goes from a regular world to a small world to a random world. Right? There's a bunch of different types of measures you can calculate about networks that I know you already had. Do you already have a class on networks? Is that right? What? Yeah, already. So you guys know all this, so I don't have to talk too much about it. But in NetLogo, there's actually a bunch of pieces of code that once you set up the network, you can automatically calculate these variables. So you can just ask NetLogo to figure out what the clustering coefficient is or the average path length or anything like that, right? 3D models. So I saw some of you actually had already played around with this because you had gotten them up and running, right? But NetLogo has a 3D version built into it, right? There's a different NetLogo 3D you get when you install. And NetLogo 3D essentially just adds a third dimension, right? And so now you can do whatever model you want, not in just 2 dimensions, but in 3 dimensions. I always like showing that's the pair box sandpile model, which is a classic model of complex systems. But quickly, just to show off another one. So there you go. Birds moving around in 3D, and then you can spin it around and kind of see where they're going, right? It takes them a little longer to flock in 3D, right, because of the fact that they have to find each other in another dimension, right? But eventually it will start flocking. One of the best ways to watch it is to follow the biggest flock. So this finds one turtle that is the largest current flock, and it looks like that flock only has like 2 turtles in it right now. But you can also follow the first turtle. Right? And this will kind of keep moving the world to follow that turtle as it moves through, right? So you can, the only difference in 3D, the exact same as doing it in 2D, except for now you have to track not just heading, but also pitch and roll, right, for the agents. And then you have to track not just X and Y coordinates, but Z coordinates as well. Okay. So besides work models and other version of 3D models, we also have GIS environments. I always these to kind of bring in real GIS data. So the GIS data is brought in not as, you can bring it in as agents, but you can also bring it into what's called the drawing layer. So in that case, it's more of just a visualization than it is an actual part of the model. But in this case, I'm having it display, I think it's like the 200 biggest cities or something like that in the world, right? Something along those lines, 200, 300 biggest cities in the world, right? But we can also bring it into the actual patches, for instance. So here, I'm having it display, I think it's like the 50 biggest rivers in the world, and it's painting them as the patches that they would go over, right? And so that kind of gives you some example of how to bring in this data, right? GIS data at this level is hard to work with, right, because it's so coarse, right? But we can do it at a much smaller level. So I'll show you one of the models that I built is kind of a toy model that was kind of fun. So this is a model of ticket sales. And it takes a little while to set up because it's actually not only pulling in GIS data, but it's pulling in census data for the United States. So what I've done is I've created a map. Does anyone know where this is? Any ideas? Huh? Manhattan. Exactly right. Right. Does it say it at the top? No. It died. I didn't know if it labeled it somewhere. It's like, but it's Manhattan, and in Manhattan we've placed a concert venue. And people have to decide whether or not they're going to go to that concert based upon how far it is away from where they live, right? And how far off in the future it is, and whether or not they want to buy the ticket now or wait until a later time when the ticket might be cheaper or more expensive, and they don't know, right? And so we can have the model run where they make these decisions, and we can kind of see where the ticket sales come from, right, over time based upon different models. And this is actually inspired by a real paper where they were looking at spatial competition for events, right? So it turns out, we always hear, I don't know, in the U.S. people often talk about the fact that, oh, that event sold out, oh, that event sold out. But it turns out the number of live events that actually sell out is very small, right? The vast majority of events, 98% of them or something like that, don't sell out, right? And so there's a question about how to properly schedule where you should, if you know your event is not going to sell out, or you have some feeling the event's not going to sell out, how do you properly choose where to have your event, right, to maximize the amount of sales you have? And there was a paper that talked about this, and I kind of stole some of the, it's not the full model, but it stole part of the model and built it into an agent-based model, essentially, for this, okay? So that kind of gives you an example of how you might use GIS data. Oh, and then the census data, so those red rectangles, those are census blocks in the U.S., right? So actually, I take that back. They're not census blocks. That's actually the road network. The blue blocks you see are the census blocks, right? And what I did was I populated each of those census blocks with one agent for every 1,000 households that actually is in that census block, right? So I'm essentially approximating at a 1 to 1,000 level the actual dynamics of ticket sales in Manhattan, right? Makes sense that way, kind of, sir? Okay. So the last thing I'm going to talk about before we take a coffee break is interactions. So there are three things that define all agent-based models: agents, the environment, and their interactions, right? And quickly, I just wanted to break down all those different types of interactions so you could think about them from a canonical way, right? So an agent can interact with itself. So for instance, and there's a model called the wolf-sheep model I'll show you, in which the sheep can check to see if they have enough energy to reproduce, right? That's a self-interaction, right? And if they do, they hatch a new sheep, right? The environment can interact with itself. In the wolf-sheep model, there's grass, and the grass decides to regrow if it's been long enough, right? There's agent interactions. Wolves can eat sheep in the wolf-sheep model. There's environment interactions. There's actually, it doesn't really exist in the wolf-sheep model, but in other models, there is spatial diffusion. So one patch can spread something to the other patches around it, right? That happens in the ants model, for instance. And there's agent-environment interaction, so the agents can interact with the environment, right? So those are the different types of actions that can occur in this space. I just want to give you a way of thinking about them when you're putting your models together, right? Now, we need to take another step back. So those are the ways we define the model, but then there's the ways we interact with the model, right? And ways that we interact with the model is something called the observer-user interface. And it's important to make sure you design this well, right? So these are where you place the different buttons and where you place the different sliders, right? And it's useful to design this in a good way that is easy for another researcher to take and use and do a different set of experiments with them. So take some thought when building your model. There's a couple of clues I'll give you, right? You want to try and align things that go together, right? So this is the small world model, and this graphs how the network properties look when you rewire one link in the network, right? And so the rewire one button is right next to that graph, right? This graph is showing what the properties are when you rewire all the buttons at a specific probability. So that graph, the rewiring probability, and the rewire all are right there, right? Now, common to both of those is the average path length and the clustering coefficient of the network. So those go in the middle between the two graphs, right? So try and keep your things together. Another thing we like to do is if there's a parameter that you can't change once the model starts running, put it above or close to the setup button, right? Because you don't want a parameter all the way down here that once you run the model you can't change because you don't know, you have to go all the way down there to look at it, right? So try and make sure that the parameters that you can't change once the model runs are higher. Daniel Kornhauser, who was one of the students I worked with at Northwestern, wrote an entire paper about how to create good visualizations or agent-based models in specific, right? And he emphasizes 3 points. Simplify the visualization, right? If there's something that's not necessary, remove it, right? Explain the components. Make sure it's obvious what each of the components of the visualization is presenting you. Emphasize the main point. All models tell a story. Make sure that the way you're writing your code emphasizes that main point as much as possible, right? So if you really want to talk about the fact that some wealthy agents go far to the right, in the simple economy model, right, then make sure that it's pretty obvious that you can see that travel, and maybe even change the model we have to color them differently, right, so you can draw attention to them as much as possible. Another thing I'd say about modeling is that, as you've probably found out already, there's 2 ways to run your models. You can run them in batch, or you can run them interactively, right? Interactively is the way I've been demoing, and where I go up and I change the parameters and I look at them. But when we start to do scientific explorations, we're actually going to want to run them in batch. We're going to run a whole bunch of models and get the results, right? And we can do that via behavior space, which I showed you a little bit the other day. Or you can do it what's called headless running, where you actually run the model without the graphical user interface. And that gets a little complex. I don't want to get into it right now, but if you go to the NetLogo model document, there's ways to do that. And almost all agent-based modeling frameworks have a way to do that. A couple of last components of agent-based models. One thing we haven't talked about is the schedule, right? This is implicit in an agent-based model. There is a series of times at which the actions occur, right? And in NetLogo, it's defined by the setup and go routines. And it can be done either asynchronously or synchronously, and we've chatted about this a little bit. Asynchronously means that agents take actions whenever they can, right? Synchronously means that they observe the world around them, decide what action they're going to take, and then take that action, right? And then another thing we need to talk about that's kind of related to that is sequential versus parallel. So sequential means each agent takes its action in turn. Parallel means that they try to all take them at the same time, right? Now, we only have sequential computers. We don't have parallel computers, right? So even when we do parallel, it's kind of fake parallelism. But there's one model in particular, if you want to take a look at, called the termites model, that actually uses a parallelism. It's just like each agent keeps running as fast as it can to do its actions, right? And tries to steal the compute time whenever it can, right? And so that's one example of doing it in parallel. And that's it. That's all I want to talk about for the components of agents. I think it's a good time to take a coffee break, and then we'll come back at 11:30 and go on to talking about visualization and some analysis of agent-based models and some examples of agent-based models that we haven't discussed yet. Okay? Thanks.